EDX Core Pure Vectors 2 Equations of Lines, the intersection of lines in 3D. So if we are looking at two straight lines in 3 dimensions, there are 4 scenarios. That the two straight lines meet each other or intersect at a single point, that the two lines are parallel and do not intersect each other ever, or the two lines are parallel and are collinear, which means they are the same straight line, or the two lines are skew to each other. So if we look at this picture on the right, if you look at the dashed lines dividing the lanes, those lines are parallel to each other and therefore they will never intersect. They are not collinear, it's not the same straight line. But if we look, for example, at the solid line down the side of the motorway and the rail across the top of the footbridge, then they are not parallel to each other, but they do not intersect, and those two lines are skew to each other. So in this example, we need to find the point of intersection of these two lines. So the first thing I would do would be to write line L1 as a single column vector. So that is 2 plus lambda. So that's the x component. The y component is simply 4, and the z component is 3 plus 4 lambda. And I do the same for the line L2. So that's minus 1 plus mu, 2 plus mu, and 1 minus mu. So for these two lines to intersect each other, these position vectors must equal each other. So if we look at the y coordinates, we have 4 is the same as 2 plus mu, so we straight away know that mu is 2. And if we sub that into the z coordinate, we get 3 plus 4 lambda is 1 take away 2, which gives us lambda is minus 1. We need to check the x coordinates. We need to make sure that we're not going to get a contradiction for the x coordinates. So we've got 2 plus minus 1 for the first line and minus 1 plus 2 for the second line, and we can see there is consistent in the answers. So we know that mu is 2, lambda's minus 1, and the x coordinates and the y coordinates and the z coordinates would all match. So to find this point of intersection, we could use the mu is 2 and substitute that into the second line. So that would give us a position vector of minus 1 add 2, 2 add 2, and 1 take away 2. Or we could have used the lambda was minus 1 and used that in the first line, which would give us a position vector of 2 take away 1, 4 on its own, and 3 plus 4 times minus 1. And you can see either method would give us the same position vector for the point of intersection. If a question wants the coordinates, the Cartesian coordinates, you should give the answer as 1, 4, minus 1 as a set of coordinates like that. So in this example, we are told that the lines L1 and L2 intersect, and we need to find the missing value of alpha. So if these two lines intersect, then I would write the first line in a nice single vector form. And the second line in a nice simple form. And we know that these two lines meet, so they must equal each other. If we look at the z coordinates first, we've got 2 plus 4 lambda is 2 mu. If we simplify that, we get 1 plus 2 lambda is mu. And if we substitute mu into the y coordinates, we get minus 1 plus 3 lambda is minus 4 plus 3 lots of, and we can substitute for mu now. And if we solve that, we would get lambda equals 0. Now we know the value of lambda, we can sub that into the x coordinates to get 1 minus nothing is alpha, therefore alpha must be 1. And there we can see a full solution for the problem. In this example, we need to determine whether or not these lines intersect. So we've got two three-dimensional lines, and the first thing to do is to quickly check whether we think they are parallel to each other. So if we take the direction vector of our first line and the direction vector of the second line, is it the case that one of these is the scalar multiple of the other? So for example, if we try to make the x coordinates match, so we make times in by minus 2, we get 4, 0, minus 2. Even though we've made the x coordinates match, we can see clearly that the y and z coordinates are not going to match, and therefore these lines are not parallel. So if these lines are not parallel, then there are only two options left. They either intersect at a single point, or they are skewed to each other. So now we can write down the equations of the corresponding coordinates. So the x coordinates would be 5 minus 2 lambda, and that would need to match the x coordinate 1 plus 4 mu. Notice the different parameters, one for each line. If we look at the y coordinates, 12 would need to match 2 minus 2 mu, and we'd need 2 plus lambda to match minus 3 plus 5 mu. So if we solve 1 and 2 simultaneously now, so if I simplify equation 2, I can have 6 equals 1 minus mu, which tells me that mu would be minus 5. So that's from equation 2. And if I sub that into equation 1, I get 5 minus 2 lambda is 1, take away 20, therefore 2 lambda is 24, lambda is 12. So things at the moment appear to be okay, but if we have a close look at the z coordinates, so if we look at equation 3 closely, we've got 2 plus lambda, which is 2 add 12, and on the other side we've got minus 3 plus 5 lots of minus 5, so we've got 14 on one side and minus 28 on the other side, and you can see that these are not equal to each other. So these lines do not meet. We know that they're not parallel, therefore they must be skewed lines. So we say that these three equations are inconsistent to each other, and hence the lines are skewed. And that brings us to the end of the session, Vectors 2, looking at equations of lines.